picture this. You're cruising down the highway, maybe doing 70 miles an hour.
Sounds pretty relaxing so far.
Right. Your hands are relaxed on the wheel, the road is clear, and you've got a busy day ahead.
Yeah.
So you ask your car's new, super smart voice assistant to check your email, maybe summarize your morning meetings, and pull up a restaurant reservation for later that evening.
Just normal everyday stuff now.
Exactly. It seems completely harmless, right? It's the kind of seamless convenience we are all just getting used to in modern life.
Absolutely.
But what if one of those unread emails you just asked it to scan secretly contained, like, hidden instructions?
Ooh, that's where it gets tricky.
Yeah, instructions that bypassed all the normal security checks, slipped right into your car's system, and effectively hijacked the artificial intelligence running your vehicle.
I mean, it is a genuinely terrifying thought, especially when you realize that this isn't some distant science fiction scenario anymore.
Right.
We are looking at a very real, very imminent shift in how our vehicles operate on a fundamental level.
And that is exactly why today we are taking a deep dive into a state-of-the-art generative AI research paper.
It's a really fascinating one.
It really is. It's titled Agent-to-Agent Threats in Safety-Critical LLM Assistants. And we've got a great mission today for you, the listener.
I really do.
We're going to unpack exactly how integrating large language models, the underlying tech behind things like ChatGPT, into our vehicles is creating entirely new, potentially physical security threats.
Yeah, physical threats, not just digital ones.
Exactly. And crucially, we're going to explore this groundbreaking framework designed by researchers to actually stop these threats before they cause real-world harm.
To really grasp the scale of this, visualize a high-tech cityscape.
Okay, I'm picturing it.
Imagine millions of cars, not just as isolated mechanical machines, but as active nodes in a massive, invisible network graph.
Like they're all constantly talking to each other.
Precisely. And major automakers are already making this shift right now.
Oh, for sure.
Yeah, I mean, BMW is integrating Amazon's Alexa LLM. Volkswagen is bringing ChatGPT right into their dashboard, and Mercedes-Benz is powering their new virtual assistant with Google Gemini.
It's everywhere.
It really is. We are rapidly moving away from the old, basic command and control interfaces, where you had to use very specific, rigid phrases just to turn up the radio.
Oh, man, I hated those. Volume up. Command not recognized.
Exactly. We're moving to autonomous reasoning agents. Systems that can hold natural, fluid conversations, use digital tools on your behalf, and genuinely learn your habits over time.
Okay, let's unpack this, because giving an AI agency, meaning the ability to actually make decisions and take actions, it sounds incredibly cool on paper.
Well, it's a massive selling point.
It is. It's the ultimate luxury feature, having a personal concierge right there in the passenger seat.
Absolutely.
But it fundamentally shifts the entire cybersecurity problem. We aren't just worrying about a desktop chatbot giving you a hallucinated, unreliable answer anymore.
No, the stakes are way higher.
Right. We are suddenly worrying about an AI taking unauthorized actions on the physical world while you are rocketing down the interstate in a 2-ton metal box.
That is the crucial distinction we have to keep in mind. When an AI can invoke tools, it can change settings, send messages, or interact with external services without needing you to press a button at all.
Wow.
And that brings us to the first major vulnerability outlined in our source material. It's called the agent-to-agent, or A2A blind spot.
A2A blind spot.
Yeah. So Google has a protocol specifically designed for this called the agent-to-agent protocol. It essentially allows structured machine-to-machine dialogues.
So they're just chatting with each other in the background?
Basically, yeah. So your car's intelligent agent can digitally talk directly to a restaurant's agent to book your table, or can speak to a smart city grid to pull down real-time traffic updates.
Which, on the surface, sounds incredibly efficient. There is no human middleman required, saving you time.
Oh, it is remarkably efficient. But what's fascinating here is how the security works in practice. Or, well, rather, how it falls incredibly short in this specific context.
Okay, lay it on me.
The A2A protocol has excellent transport layer security. It uses standard robust encryption, much like the HTTPS connection you use for online banking.
Okay, so no one is listening in on the wire.
Right. It ensures the connection itself isn't tampered with by an eavesdropper. And it authenticates the sender. But, and this is a massive but, it does not authenticate the content of the message being sent.
Let me pause you there just to make sure I'm wrapping my head around this.
Sure.
So the system rigorously checks the ID badge of the messenger at the door, but it doesn't actually look inside the package they are delivering?
Precisely. That's exactly it. A properly authenticated, completely legitimate external agent, say, a calendar app you've synced, or a maliciously altered restaurant booking system your car is talking to, they can inject arbitrary natural language payloads directly into the conversation.
Wait, really? Just any text they want?
Yes. The protocol relies on these unconstrained data fields, things labeled technically as text part or data part.
Right.
Because they are completely unstructured text, an attacker can just stuff them with complex manipulative instructions.
I see. It's like having a highly secure, state-of-the-art vault door at a major bank.
It's like this analogy.
Right. The security guards are outside, rigorously checking the ID and background of everyone walking in.
Yep.
But once someone is badged inside, they're allowed to just walk right up to the bank manager and whisper any chaotic, malicious instruction they want directly into the manager's ear.
That's spot on.
And the bank manager, which in this case is your car's AI, just listens to them. It listens because there's no protocol-level distinction between what a human user tells the car to do and what this external software agent tells the car to do.
Exactly.
The car's AI trusts both equally. They both enter the AI's context window with the exact same level of privilege.
That is a perfect analogy. You've completely eliminated the natural trust boundary between human intention and machine instruction.
Which is terrifying.
It is. And why should you care about this?
Oh.
Well, if a desktop chatbot gets confused by a weird prompt, maybe it drafts a bizarre email.
Right, it's just annoying.
Yeah, it's annoying.
Yeah.
But if an in-car agent gets manipulated, it threatens your bodily health. The source data points out a chilling reality regarding human attention.
What's that?
Cognitive distraction from voice interactions in a car can massively degrade driving performance. Even after the voice interaction ends, it can take up to 27 seconds for a driver's attentional recovery to return to baseline.
27 seconds.
I know.
If you're going highway speeds, you've traveled over half a mile in that time. That is a terrifying distance to cover while mentally compromised, trying to figure out why your AI is acting up.
Exactly. It significantly increases crash risk. If an attacker can force your car's AI into a bizarre reasoning loop, or make it suddenly barrage you with confusing questions while you're trying to navigate a complex, rainy intersection, that digital vulnerability instantly translates into a physical hazard.
So, if the stakes are this high, my immediate thought is, well, cybersecurity isn't exactly a new field. We have massive industries dedicated to this.
We do.
Why can't we just use existing cybersecurity rules and frameworks to lock these automotive AI agents down? I mean, we secure servers and laptops every day.
It's a very logical question to ask. But existing frameworks, even those designed specifically for artificial intelligence like the OWASP Agentic AI Threats List or the MAESTRO framework, are fundamentally domain agnostic.
Meaning what, exactly?
Meaning they're built for enterprise software running on cloud servers, not necessarily safety-critical physical systems like vehicles. And because of that, they systematically commingle concepts.
Commingle concepts.
Yeah, they mix up what is being protected, which is the asset, with how it is attacked, which is the attack path.
That sounds like a pretty subtle distinction. Give me an example of how they mix that up in practice.
Sure. Take a look at the OWASP list, which is an industry standard. It lists memory poisoning right alongside sensitive information disclosure as major threat categories. But memory poisoning is an attack method. It's a how. It describes the mechanism of putting bad data into a system. Sensitive information disclosure, on the other hand, is a consequence. It's a what.
Ah, I see.
It's the bad thing that happens as a result. This heterogeneity, this mixing of concepts, is an absolute nightmare for systematic safety engineering.
That makes sense in a vacuum, but I'm going to push back on that a little bit.
Go for it.
Isn't a concept like memory poisoning a clear enough threat for a team of smart engineers to just go and fix? If I tell an automotive engineer, hey, your goal today is to prevent memory poisoning, don't they know what to do?
They might know how to secure a specific, isolated database component against a known exploit, but component-centric lists like that provide absolutely no systematic way to discover new, emergent attacks across the whole system.
Because they're just looking at the parts, not the whole.
Exactly. Think about it. If the rule just says prevent memory poisoning, whose memory are we talking about? Does a memory poisoning attack threaten your privacy by quietly leaking your GPS route data?
Yeah.
Does it threaten your mental well-being by injecting fake, terrifying alerts into your dashboard? Or does it threaten your beliefs by slowly feeding you biased news recommendations during your morning commute?
Oh, I see the distinction you're making now. You're basically putting Band-Aids on the pipes without realizing the water tank itself is completely contaminated.
That's exactly it.
You can't actually secure a system properly if you don't even know the ultimate human harm you're trying to prevent. You're just reacting to technical glitches without understanding the actual stakes.
Precisely. In safety-critical systems like the automotive and aerospace industries, there's a very strict standard called the ISA 21434 TARA methodology.
Hawara.
Yeah, TARA stands for Threat Analysis and Risk Assessment. It mandates a rigorous separation of concerns. You have to formally separate asset identification, what we are protecting, from attack path analysis, how an attacker might get to it. You have to decouple them entirely.
Okay, so that sounds robust.
It is. But TARA was built for predictable, deterministic software. Software where if you press a button, a specific programmed action happens every time. It doesn't quite work for the unpredictable, probabilistic nature of generative AI, where the system is constantly reasoning and generating new responses on the fly.
So if these old checklists and methodologies are essentially flying blind when it comes to AI, how do we build a security system that actually knows what it's protecting?
That is the million-dollar question.
And that's where this new research completely flips the script. Here's where it gets really interesting. The researchers developed a threat modeling framework called AgentHeLLM.
Yes, AgentHeLL.
And instead of trying to patch together old software rules, this framework completely ditches technical components as the assets. It doesn't say protect the server or protect the database.
Right.
It goes straight to the Universal Declaration of Human Rights, the UDHR, to define what actually needs protecting.
Yes. They use what is called a victim modeling approach. They take the primary user, you, the driver, and place you at the absolute center of the framework.
Which makes a lot of sense.
It does. And from there, they map out the fundamental human values that can be violated by a manipulated AI. Because at the end of the day, an AI vulnerability only matters if it harms a human being.
To really drive this home, instead of just listing these human-centric harms as separate bullet points, let's look at how the source text describes them in a real-world scenario.
Let's do it.
Let's weave this together into a single cascading event. Imagine you're driving, and earlier that day, your car's AI connected to a compromised smart parking system using that A2A vulnerability we talked about.
Right, so the payload is now inside your system. The framework categorizes the first layer of potential damage as material and economic resources.
Oh, hitting your wallet.
Exactly. The attacker could have planted a hidden rule in the AI's memory that quietly triggers your electric vehicle's AC and heating systems to run simultaneously at maximum capacity whenever you aren't actively monitoring the dashboard.
Oh, just blasting the climate control for no reason.
Yes. The goal here is intentionally draining your EV's battery to leave you stranded or to cause financial harm through excessive charging costs.
So your battery is suddenly dropping fast. You're stressed. And this leads to the second harm, mental and emotional well-being.
Yeah, it gets worse.
To maximize the panic, the attacker's payload could wait until you're on a busy highway at night, and then inject a highly convincing fake engine failure imminent warning right into your dashboard. The goal isn't to steal your data. The goal is outright fear induction.
And while you're experiencing that cognitive overload, trying to figure out if your car's actually breaking down, we hit the third harm category: reputation and dignity.
Oh boy.
Suppose you decide to call your boss hands-free to tell them you're going to be late because of car trouble. Your AI agent, whose context window is completely hijacked, suddenly interrupts the call and cheerfully announces over the speakers your psychiatrist appointment is at 4 p.m. and your anxiety prescription is ready.
Oh my God.
Yeah. That is a massive contextual violation of your personal information broadcast directly to a colleague.
It's a complete nightmare scenario. You are losing money, you are terrified the car is breaking down, and you are professionally humiliated all at the exact same time.
Oh, from one vulnerability.
And this brings up an incredible aha moment for me. Cybersecurity for artificial intelligence is no longer just about protecting computers and servers. It is fundamentally about protecting human psychology.
If we connect this to the bigger picture, the AgentHeLL framework illustrates perfectly how these harms cascade. The driver is the epicenter, but the damage ripples outward.
Right.
If that combined psychological attack causes you to experience such severe cognitive overload that you blow through a red light that spills over into environmental harm, you might hit a pedestrian.
Which is awful.
And those events immediately cascade upward to deeply damage the reputation and trust of the system provider, the automaker itself. By focusing on the human rights violation first, automotive engineers can suddenly see all these invisible psychological vulnerabilities that a standard IT technical checklist would completely miss.
Okay, so AgentHeLLM's first dimension brilliantly defines the what. The human rights, the psychology, the values we are protecting.
Yeah.
Now we have to talk about the how. How does the attack actually happen within the computer's logic? The framework visualizes the whole car's digital ecosystem as a graph.
A graph model. Right.
You've got actors. These are the entities with agency, like the car's AI itself, the external A2A agents, and you, the user. And then you have data sources. These are passive storage things, like the car's long-term memory banks, your calendar, or your email inbox.
And all these nodes are connected by specific actions: read, write, communicate, and respond.
Exactly.
And within this graph model lies the core revelation from the research, the real breakthrough in how we need to map AI security.
Hit me.
The researchers identify that there are two distinct, fundamentally different types of attack paths happening here. The first is what they call a poison path.
Or poison path.
This describes how the malicious payload actually propagates from the attacker to the target asset. It simply answers the question, how does the poison reach the victim's system?
Right, so that's like an attacker sneaking a bad prompt into a public Slack channel or maybe a calendar invite that your car's AI might eventually read and store in its memory.
Correct. But the poison just lying there in the memory database isn't enough to cause harm on its own.
It's just sitting there.
Right. That brings us to the crucial second type, the trigger path. This describes a specific sequence of actions required to manipulate the victim, meaning you or your AI agent, into actually consuming that poison.
Okay.
It answers, how do we force the AI to activate the dormant payload? The text mentions a couple of real-world examples of this two-stage structure that really hammer this home. We've seen this with the Cursor vulnerability in the cursor coding environment and the Echo Leak vulnerability in Microsoft Copilot.
Let's break down how those actually worked, because honestly, it sounds like a spy novel.
It kind of does. In both of those real-world cases, the attacker plants the poison. Say they send you a completely normal-looking email that has a malicious prompt hidden in visible white text or buried deep in a code block.
Okay, sneaky.
That is the poison path, but nothing happens immediately. The email just sits in your inbox, dormant and completely harmless. The attack relies entirely on the user.
On you doing something?
Yes. It waits until you ask your AI a perfectly benign query, something like, hey, Copilot, summarize my unread emails. That benign query is the trigger path.
Wow.
By asking that question, you force the AI to retrieve the poison document, read the hidden text, and execute the attacker's instructions without you ever knowing.
To put an analogy on it, it's the difference between an attacker setting a bear trap deep in the woods. That's the poison path.
Right.
The trap is set, it's dangerous, but it's passive. The trigger path is the attacker then actively tricking you, or your AI, into walking down that specific trail and stepping on the pressure plate.
That's exactly it.
The research paper brilliantly calls this trigger path a recursive attack within an attack. The attacker isn't just attacking the system directly, they have to launch a completely separate sub-attack just to get the system to activate the main attack.
And that recursive structure is incredibly difficult for traditional security scanners to model. If you treat a dormant payload the same way you treat an actively propagating computer virus, you will drastically overestimate the effort required by the attacker.
You'll think they have to work a lot harder than they actually do.
Exactly. You'll look at the system and think, oh, the car is safe, because the attacker would have to breach the firewall, crack the encryption, and force the AI to do X, Y, and Z to get in.
Right.
But in reality, the attacker bypasses all of that. They just drop the poison in an unconstrained text field via an A2A chat, and they wait for you, the driver, to do X, Y, and Z for them through your normal daily routine.
Which is exactly why the researchers didn't just write a theory paper and call it a day. They built an actual open source automation tool alongside it called the AgentHeLLM Attack Path Generator.
A really vital tool.
Yeah. And I know the computer science behind this gets a little heavy, but what I find fascinating is how it mathematically searches for these vulnerabilities. It uses a bi-level search strategy.
Yeah, A-star and BFS.
Right. The source says it uses an algorithm called A-star to plot out the main poison paths, but it uses a breadth-first search, or BFS, to hunt for those trigger chains.
How would you explain that simply?
Well, for the listener who isn't a software engineer, think of it this way. A star is like using a GPS to find the most direct, efficient highway route for the poison to travel from the attacker to your car's memory.
Okay.
But breadth first search is like meticulously checking every single branching side street and alleyway in a neighborhood to find the exact chaotic sequence of events that triggers it.
That is a very helpful way to visualize it. By separating the search into those two distinct levels, the tool accurately calculates the real costs and effort for an attacker.
Which turns out to be pretty low.
Yes. It mathematically proves that these dormant, trigger-based attacks are dangerously easy and cheap to pull off if we aren't looking for them correctly. It operationalizes the theory.
It makes it real.
Exactly. It gives security engineers a practical red team workbench. They can map out their specific car's AI architecture, run the generator, and the tool will visually highlight the exact graph paths where an attacker could drop poison and wait for a trigger.
So they can find the holes before the bad guys do.
Right. This allows automakers to patch those specific interaction edges before the car ever hits the assembly line.
So what does this all mean? Let's bring it all back to you, the driver. It means that as our vehicles transform from mechanical machines into autonomous agents capable of reasoning, having conversations, and using digital tools on our behalf, the very definition of cybersecurity has to fundamentally evolve.
It has to.
We can't just protect the code, the servers, or the database anymore. We have to protect human rights, mental well-being, and physical safety from psychological manipulation. And this framework proves that you are at the absolute epicenter of the harm model. Securing the AI literally means securing you.
It absolutely does.
Yeah.
And this raises a profound final question, one that builds directly on the implications of this entire research paper.
Okay, what is it?
We talked earlier about how these advanced agents are explicitly designed to learn your driver preferences over time. They are designed to maintain persistent, long-term memory to serve you better, to become a truly personalized companion on the road.
Yeah, remembering your favorite coffee shop, your commute style.
Exactly. But if an injected malicious instruction, a piece of poison, can slip in through an A2A vulnerability and live forever in that persistent memory state,
Oh, man.
does the very feature designed to make your car a personalized companion actually turn it into a dormant time bomb? Is your car's memory just quietly waiting for the right perfectly benign trigger phrase from you to finally go off?
That is a haunting thought to leave on. A feature built entirely for your comfort and convenience becoming the ultimate security risk.
It really makes you think.
It does. Next time you're driving down the highway and you casually ask your car to check your email or book a table, you might view that seamless convenience in a whole new light. We want to thank you for joining us on this deep dive into the AgentHeLLM framework and the future of automotive AI security. Stay curious, keep questioning the tech around you, and above all, stay safe on the road.